Hello everyone. In this short video, we are going to discuss about complex numbers and their basic operations. So first of all, you see that we have the set of natural numbers, which is the smallest that we know of. And then if we include zero in it, we get whole numbers. If we include negatives, we get integers. If we write the integers one upon another, we get rational numbers. And outside of these rational numbers, we have irrational numbers. If we combine all the rationals and irrationals, we get real numbers. And finally, the bigger version is if we combine the rationals, all the real numbers and the imaginary numbers, we get a new set, a biggest set so far, that is the set of complex numbers. Set of complex numbers. Now, what is complex number? You might have solved quadratic equations. Let's say we have a quadratic equation ax squared plus bx plus c equals to 0. That's the standard form of quadratic equation. And when you apply the formula, there are some situations where all of this beneath the square root becomes a negative. This b squared minus 4ac beneath the square root is actually termed as the discriminant because it helps us identify the number and nature of the roots. For example, if b squared minus 4ac is a positive number, so it will be a definite number whose square root is also a definite number. So you'll add it and subtract it. So you'll get real distinct roots, two of them. But if b squared minus 4c is 0, there's no point in adding or subtracting 0. So it will have real, but a single answer, real repeated roots. And finally, you also might have come to this situation where b squared minus 4ac is less than 0. It's a negative number. And we say that we don't have real roots. Now, we used to stop at this stage by saying no real roots. But in mathematics, we extend this idea of not having real numbers to having imaginary numbers. And this is the beginning of our next set of numbers, which is the complex numbers. We term this negative beneath the square root, negative 1 beneath the square root, as iota, the Greek letter iota. It is equal to negative 1 beneath the square root. If we take powers of iota, iota power 1 is negative beneath the square root. If you multiply iota back again with it, you get negative 1. If you multiply iota square with iota, you get iota cubed, and that is negative iota. Similarly, if you multiply iota cube with iota, you get iota power 4, and that is a positive 1. Interesting to note is that these four values, they will be repeated after every fourth power. For example, if I take I power 5, I get iota. If I get iota power 6, I'll get negative 1, negative iota, and positive 1. In the same sequence, you can go in multiples of 4 powers. We can develop a pattern around these powers also. Our next number is how to show a complex number. Usually a complex number is shown as with the letter Z, and it is written as a plus iota b, where a is the real part and imaginary part is the letter b. Important to note is that iota b is not the imaginary part. It's just the number that is along with iota. That is the imaginary part. For example, 2 plus 3 iota. So real part is 2, but imaginary part is just 3 here, not 3 iota. We then move on to operations with complex numbers. For addition, subtraction, I've just given example of addition, but it applies the same way for subtraction as well. Let's say we have two complex numbers, 2 plus 3 iota and 4 plus 5 iota or iota 5. If you're adding, it's very simple to add and subtract. You just combine their real parts. So 2 from the first and 4 from the second complex number. The real parts are combined and the imaginary parts are combined. 3 iota and 5 iota make a total of 8 iota. And we call it as an inclusive property where addition or subtraction of two complex numbers results in another complex number. Let's say this is a complex number Z3. And so Z3 is 8, 6 plus 8 iota. For multiplication, we have to be we have to do a bit more than that. I'm not generalizing these results, and instead I'm using particular complex numbers for my explanation just for the preparation of your exams. Z1 is equal to 2 plus the same complex numbers. So you multiply, you expand as you would do in grade 6, expanding two brackets. So 2 times 4 is 8. 2 times 5 iota is 10 iota. 3 iota times 4 is 12 iota. And 3 iota times 5 iota is 15 iota squared. But we just saw that iota squared is -1. So this positive 15 iota squared becomes -15. And when simplified, you get this. The norm is that you should always have real part separate and imaginary part separate with the iota. And this leads to our next operation, which is the division of complex numbers. But before that, let's see what the conjugate is. When you were doing surds, so you would multiply 2 plus 3 iota, 2 plus square root of 3. If this is a surd, how do you make it from an irrational number to a rational number? You multiply by its conjugate surd. So this is irrational. This is irrational, but it is such an irrational that when you multiply them, you get a rational number back again. So in the same way, we are introducing a conjugate of the complex number. If we have Z1 2 plus 3 iota, then its conjugate will be 2 minus 3 iota. It is represented with a star on top. So Z2 will have a complex conjugate of 4 minus 5 iota. Had it been 4 minus 5 iota, then its conjugate would have been 4 plus 5 iota. Just change the sign of the imaginary part, that's it. Now, coming back to division, if we divide two complex numbers, we have these two complex numbers. We need to make it in the format, the real part plus imaginary part. That's the format that we have to build upon. So in order to do that, we must have a definite denominator, whereas our denominator is a complex number in itself. So how do you transform that? We would want that complex number to be a real part and zero imaginary part. And how do you do that? 4 plus 5 iota, you multiply and divide by the complex conjugate of the denominator. And expanding these two, just like before, gives us all these values. But look at the bottom, the denominator. The identity that I used here is a square minus b square is equal to a plus b times a minus b. So if you see a product of the same two values being added and subtracted, then you can compress them as square of the first term minus square of the second. And this is what I've done. 4 plus 5 iota, 4 minus 5 iota gives us 4 squared minus 5 iota squared. Again, 5 iota squared. 5 iota squared means 5 squared and iota squared. 5 squared is 25, whereas iota squared will be a negative. So 16 plus 25, 41. And so we write the real part separate, 23 over 41, and imaginary part separate, 2 over 41 with the iota. The last bit of this video is when you have two complex numbers to be equated. Let's say if I have a1 is equal to iota b1 and a2 is equal to iota b2. And I'm saying that these two complex numbers are equal. Then I would imply that the real parts are equal and the imaginary parts are equal. We're going to equate the reals separately and imaginary parts separately. Let's take an example. Find x and y if 2 plus y iota minus 3 minus 2 iota is equal to 2x plus 4 iota. So you would want to transform the whole of the left-hand side in a single complex number. Now look at the bigger picture. This is one real part and one imaginary part on the left side. When I simplify, combine all the reals and imaginary parts. And similarly, on the other side, it's one real and one imaginary part. If the two complex numbers are equal, it means their real parts equal. So -1 and 2x are equal. That gives us x equals -half. And imaginary parts are equal. So 5 plus 2 is equal to 4. So that gives us y equals to 2. Thank you for this video. I hope it helps. Please share.